It's now recording. All right, team. So here we go. Let's recap. Tan graphs. Tan graphs. What is the period formula for a tan graph again? Can I please have Jason? It is pi on n. So write it down if you've forgotten. Pi, or for tan graphs, it does not take 2 pi revolution, or one revolution does not take 2 pi to actually make one cycle again. It's pi, whereas sine and cosine is 2 pi on n. Okay, so sine and cosine, the period is equal to 2 pi on n. That's the difference. Another difference between tan and sine and cosine. Tan, does it have any amplitude? Any amplitude for a tan graph? No, Christina shakes her head. There is no amplitude. The graph, which is nice, that means you don't have a maximum or a minimum that you have to worry about. The graph goes infinitely up and infinitely down. So that's the shape of a tan graph. So let's remind ourselves again. Sine starts from the center. Cos starts from the maximum, comes back to the maximum. And then tan has this shape. But remember, the periods are different. So tan should be a bit thinner, okay, because it's only pi period. So you got 3 shapes there. Today's lesson, or I'm just reinforcing what you've learned previously, we're doing tan graphs, and I gave you an asymptotes formula. A formula to find out all the asymptotes again. What was the formula, if you remember? Let's go into Murphy.
2k plus 1 times pi over 2.
Beautiful. 2k plus 1 just means make it odd, because we realize that the tan, to get an asymptote, means it has to be undefined. It's only undefined at every 90 degrees. But 90 degrees is pi on 2, 3 pi on 2, and then 5 pi on 2, 7 pi on 2, 9 pi on 2. So we realize it's every odd pi. That's what 2k plus 1 does. Okay, so whatever k is, it'll make it even by doubling it. Add 1 makes it odd. So here's my odd pi, but it's every odd pi on 2. Because 90 degrees is pi on 2. So multiples of 90 degrees is multiples of pi on 2. But it has to be odd, not even. And then it gets affected by a dilation, just like your period. You had divided by n, or technically it's times by 1 on n. That's why you have this n on the bottom. So it's just saying that whatever the number in front of x is, or n, whatever n is, that shrinks the graph. And if it shrinks the graph, it shrinks the asymptote. That's why the n is there. Okay, so I'm just saying every odd pi on 2, so every 90 degrees, and the 90 degrees could change depending on dilation. That's what the formula is. So I told you that all you need is the period, and if you know the first asymptote, you can find the rest. So let's do it. The period in this case is pi on n, and n in this case is equal to what? Let's go with Artie. What's my n value in this tan equation? What's n? 2. So it becomes pi on 2 is your period. That means that to find the asymptotes, we have a rule now. It is 2k plus 1 pi over 2 times 2, which is 4. Okay, because we now know n is 2. So 2 times 2 is 4. So you've got a formula now to find your asymptotes. And I told you the easiest one is just make k equals 0. Get your first one. So here we go. If k was equal to 0, very first asymptote, then the equation for your asymptote is x equals 2. 0 times 2 is 0, plus 1 is just 1. 1 times pi becomes pi on 4. I now have my first asymptote. So let's look on the axes here. I know they haven't given you any numbers there. And usually a general tip when you're sketching sine, cosine, or tan graphs, a tip is if you work in the scales of 12ths, it's generally possible to do all types of graphs. Because think about it, you've got pi on 3, pi on 4, pi on 6, pi on 2. Lowest common multiple of 3, 4, 6, and 2 is 12. So that's why if you work in 12s, it doesn't matter. You'll always be able to calculate or like make it evenly nice. Okay, so if you're ever in doubt, make the scales out of 12s and you should be okay. So here we go. I'm now going to have a look at the problem here, and I'm just going to go, what's the... oh, I shouldn't have given you the asymptotes. Sorry. I gave you the wrong domain, but that's okay. The domain, I would have preferred it to be negative pi to pi, but that's all right. 0 to 2 pi is good too. So 0 to 2 pi, let's do it. I'm going to call it pi on 12. So do it out of 12s. Then you got 2 pi on 12. I know I can reduce it, but I'm just keeping it as 1, 2, 3, 4. So here's my 3 pi on 12. Here's my 4 pi on 12. Here's my 5. I'm just going to write 5, 6, 7, 8, 9, 10, 11, 12 pi on 12 is really where your pi is. Okay, so I'm going to change that to pi. Then you got 13 pi on 12, 14 pi on 12, 15 pi on 12, 16 pi on 12, 17, 18, 19, 20, 21, 22, 23, and then again 24 pi on 12 is the same thing as saying 2 pi. So I'm going to highlight it as these are your two key spots. Cool? So I've labeled the axes. If you stick with the 12s, generally whichever graph you choose will generally look pretty nice. Yeah? Now I said the first asymptote, we said the first asymptote is that x equals pi on 4. Now if it's all out of 12s, which one is it? Pi on 4 is the same thing as something out of 12. Oh my God. Times by 3. So top by 3. 3 pi. Can I get a show of hands that you knew that, but you were just afraid to say, or you actually didn't know? So show of hands you knew that, but you just didn't say. Okay, good. I was just worried about your fractions. If fractions is one of those things, you really got to practice it for this chapter. Okay, so if you're not really sure of fractions, this is a great time to practice again. But 3 pi and 12 is over here. So here we go. I'm going to highlight it down. Oops. Wrong column. Here's my 3 pi and 12. Here's your first one. X equals 3 pi and 12. Great. Now, you know how I said tan graphs are really easy once you know your asymptotes? Well, to find the next asymptote, you just add on the period because that's how long before it recycles again. So if it recycles for every period, the period is pi on 2. So all you're really working out is what is 3 pi on 12 plus pi on 2? Fractions again, for those who struggle with fractions. Can't add them unless denominators are the same. So here we go. Times this by 6 to get the 12 times the top by 6. So you already know every time you add on the period, you're just adding on an extra 6. So here we go. Let's add 6 every time. 3 plus 6 gives you 9. So here we go. Here's my next asymptote at 9. There's my next asymptote at x equals 9 pi on 12 plus another 6 to get to your next asymptote. So here we go. 9 plus 6 is 15. X equals 15 pi on 12. And then if I go to the next one, what is that? 15 plus 6, 21. And I get x equals 21 pi on 12 is my next asymptote. And then 21 plus another 6 will now be too far. It will bring us to, whoops, what's happened there? It will bring us all the way past our domain. So we know now 21 plus 6 would have gave you 27, but remember that's 24 there. So 27's much further away. All right? So that means your graph. Now, if you think about the graph, tan graphs have this shape. You can either have the shape that looks like this. See, once you've got the asymptotes, it can look something like this. And that's all you do. You just follow wherever it is, but we know that the asymptote has to be somewhere over there. We just don't know where the x-intercepts are. Right? So all we need now is we have a y-intercept, x-intercept. You can predict what it looks like. But the other nice thing is, look at the equation. Do I have any vertical translations? Because if it was just horizontal, you can already tell where the x-intercepts are. Do we have any vertical translations? Yes, we do. Vertical translation of root 3. It's gone up by root 3. If it's gone up by root 3, that means on your graph. Now root 3, roughly, how much is that? Where is it between? Because you have to be able to distinguish roughly how much has gone up. Has it gone up this far, so it looks like this? Has it gone up this far, so it looks like this? Where is root 3 roughly, Anthony? Yeah, something there, because we know that root of 4 is 2, so therefore it has to be less than 2. But root of 1 is 1, so if it's root 3, it must be somewhere between. It's probably closer to the 2 than it is to the 1. So I expect it to be somewhere in between. What I don't know is where's the center? So where is the middle? Now, you know it goes up by root 3. Up by root 3. Reading the graph. Does it move left or right? How do you know again? How do you know if it moves left or right again? What did I teach you guys? Yeah, well, not let x equal, let this equal to 0. Okay, so whatever your function is, where the x's are, 2x minus pi on 3, if you want to know if it moves left or right, that's the one you let equal to 0. So let's solve it. Let this equal to 0, move it across. Here we go. 2x minus pi on 3, we want that to equal to 0, so let's solve for x. 2x will equal to pi on 3, divide both sides by 2. What does that mean? If x is positive, right or left? Moves to the right. I'm just going back to getting you to practice reading the graph because it helps you visualize what the graph looks like. So I'm moving to the right by 0.6 if it's a positive. If you solve for where the function is, see it's tan of whatever that is. It used to be where x is, tan of x. Whatever that is, if it ever changes, that's to do with x transformations. That's what we learnt in our previous chapter in chapter 7. So I taught you a quick way to work out if you move left or right. I said 2x minus pi on 3, whatever that is, let it equal to 0. Solve for x, it moves to the right if it's positive, moves to the left if it's negative. And the proof to it was transformations. So if you went back and you worked on your mapping notation, you'll be able to see why I know it's to the right by 0.6. Okay? So why does that matter? Well, pi on 6, if I'm moving to the right by pi on 6, let's change that to out of 12s because we made our scale out of 12s. That means it's actually 2 pi out of 12. That's where I've moved. I've moved the graph to the right by 2 pi on 12, and I've gone up by root 3, and root 3 is probably somewhere there. So in a general sense, if I asked you to sketch the graph now, we know it looks something like this. I just don't know where the where the endpoints are. I haven't worked out the endpoints, but I got a general idea that it's every 2 pi on 12, and you add on 6. You add on 6 pi because that's the period, and you know where the centers are. So the center now has gone. Remember, you said up by root 3 to the right by pi on 2 pi on 12. So to find the next one, just add on a period. And we said the period was pi on 2, and we worked out it's every 6. Because pi on 2 is the same thing as 6 pi on 12. So add on 6 every time. So here we go. 2 pi plus 6 gives you 8. So it's over here. Plus another 6. What's that? 6, 14. And really, you notice there's a pattern. It's one short of the asymptote every time. So it's somewhere over here each time. 24, 23. No, that doesn't look right. No. 20 plus, 26 is on that side. So if you look at the shape of the graph now, can you see, how come it's so skewed? Something's off. Oh, because I drew it skewed. Oh no, but then even the asymptote is weird. Did we read something wrong? Pi on 3 divided by 2, pi on 6. Pi on 6 is 2 pi on 12 plus root 3. That's right. Why does it look so funky? Oh, maybe it looks like this. Like it's not even. So it might be like that and it goes on infinitely. So then center is definitely still here. So it must be like that. So it means the graph likely, the y-intercept must be a very negative answer from what I'm seeing. So as you can see, once you have the asymptotes it's actually really easy to draw the graph and then predict roughly where it is. But can you see all I'm missing now is if I've got a y-intercept of the graph, if you get a y-intercept of the graph, you'll know how far the graph should come out. But based on the logic at the moment, these points gives you an idea of where you stop the tan graph. And there's only one x-intercept. Once you find the first one, you're out on the period. Each one, I've only found the first one. So I found the asymptote, just one of them. I found the very starting point by reading up, down, left, right, and I just add on the period. Now if I find the x-intercept, I just find the first one and I add on the period, and you get the entire shape of the graph. And if you keep it out of 12s, it's a nice perfect shape. Does that make sense? Okay, so the tan graphs are much easier just because you only need to find one answer for each one. Find one x-intercept, find one asymptote, find one starting point, add on the periods, and you're able to then picture what the graph looks like. The only things I'm missing are y-intercept and endpoints, because it starts from 0 to 2 pi, so I need to know when x is 0 and when x is 2 pi, what are my y values, and that really adjusts how far my graph should look. Okay, so let's work out those points. X-axis intercept, let's start off there. So I've got a prediction now. We expect about 1, 2, 3, 4, and maybe 5 potentially. I reckon there's a fifth one. There's potentially 5 x-intercepts. Here we go. Let's calculate. Let's practice your solving equations. So let y equal to 0. 3 tan of 2x minus pi on 3 plus root 3. Let's do this, team. Here we go. So to find x-intercepts, you let y equal to 0. We got 3 tan of 2x minus pi on 3. Let's solve it. What do I get rid of first? I'm trying to solve for x. What are you going to get rid of? Root 3. Bring the root 3 across, divide the 3, and what you'll get is you get negative root 3 over 3 is equal to tan of an angle, so 2x minus pi on 3. And this is where you have to go back to think about your unit circles and your exact values and symmetry properties. Here we go. Tan inverse both sides, so you get 2x minus pi on 3 is equal to the tan inverse of negative root 3 on 3. So, that's saying tan of what angle will you have a negative? So where is tan negative again? Which quadrants? Which quadrants will tan be negative? We've got not 4. Remember, positive gradient is this way. Oh, no, you were right. I'm wrong. 4. That's right. Quadrant 4. What else? 2. Very good. These are the two quadrants where the gradient is clearly a negative gradient. And you're asking, well, now go through your exact values, the hand method. Tan of what angle will give you root 3 on 3? Root 3 on 3 is the same thing as 1 on root 3. Yeah. So you think about it. And then the reason why I gave that to you to remember is because you want 1 sine finger on the top and 3 cos fingers on the bottom. Can't have 3 sine fingers and 3 cos on the bottom unless you have 6 fingers. Yeah. So sine needs to be on the top. So the only finger that works out that you have 1 sine finger is 0.6, which is 30 degrees. So I now know the base angle or the reference angle. We now know it's 30 degrees, but this has to be pi and 6, and this has to be pi and 6. Going from 0 to 2 pi, so 1 revolution as I rotate, you can see here, rotating all the way to get to my first solution, but I'm just short of it, short of pi, but pi and 6. So my first solution should be pi minus pi and 6, pi minus pi and 6. And the other one is short of 2 pi just by pi and 6 as well, so it's 2 pi minus pi and 6. Quick working out. Pi minus pi and 6 gives you 5 pi and 6, good. And then 6 times 2 is 12. 12 minus 1, 11 pi on 6. Right now I still have 2x minus pi on 3, so this is all the transformations that's applied. So now we're going to do it. Plus pi on 3 on both sides, divide everything by 2, so let's go. Plus pi on 3. This is where I think most students generally struggle, just mainly because of fractions. It's not actually the concept, it's just whether you can add fractions or not at this point. Let's work it out. 2x is equal to 5 pi on 6 plus pi on 3 times both bottom and top by 2. So that's like adding on 2. So 7 pi on 6, and you get 13 pi on 6. Divide everything by 2. You get 7 pi on 12, and you get 13 pi on 12. And this is one of the beauties of keeping your scale out of 12s. You'll generally capture all of the possibilities. Okay? Now these are my two possible x-intercepts. 7 pi on 12, 13 pi on 12. So let's look at the graph again that we drew. 7 pi, hey, oh, it was pretty close. Look at that. I made a guess. That wasn't too far. 7 pi on 12. And we had the other one as well. See that? So you get an idea of roughly where it is once you've got the asymptotes, one starting point, and then one x-intercept. But here we go. So let's put in our x-intercepts now. So I'm going to put in the x-intercepts. We now know the first x-intercept was at 7 pi on 12. Here we go. So 7 pi on 12. That's my first x-intercept. Now to find all the other x-intercepts, we already said, add on a pi. Add on the period. What was the period again? Yeah, pi on 2. This is our period, but we converted it before. Pi on 2, since it's all out of 12 scale, you just change the pi on 2 to 12s. So if you change it to 12s, that's 6 pi on 12. So you're really just adding on 6. So if you started off at 7 pi on 12, add on another 6. 6 pi on 12, that's how you get to 13. And then 13 plus 6, 19. 19 plus 6, 25. But can you see how I'm finding all the x-intercepts? I just found 1. I didn't even need to find 2 like I did at the start. You just need to find 1. That's it, just 1. And you add and subtract the period. So here, if you wanted to know all your possible answers, add all the 6's until you pass the domain and minus 6 until you pass the domain. So 7 plus 6 gives you 13. 13 plus 6 gives you 19. 19 plus 6 gives you 25. Now you're beyond the domain. Domain was 2 pi, so it had to be 24 out of 12. Then you minus go backwards. Minus 6 gives you pi on 12. Minus 6 again, and you get negative 5 pi on 12 out of the domain. We said from 0 to 2 pi. So what are my acceptable x-intercepts? There's only 4 there, which is what I said before. I predicted it's either 4 to 5 just based on our assumptions. So on your graph here, we can actually put it all in. Here's 1. Here's 2. Here's 3. The next one, 13 plus 6 is 19. So 19 is over here. And then 19 plus another 6 is way beyond. So there's my 4. So you got all the points. I only found, how did I find again? Let's recap. I found the starting point by reading up, down, left, right. So I said up by root 3 to the right by pi on 12. There's my first starting point. Asymptotes, you use one formula. I gave you 2k plus 1 times pi over 2n. I found the first one. Then to find the x-intercept, I just showed you, we're just doing exact values and symmetry properties. You find the first one, which is over here. And then all you have to do for each one was add on a period. The period was pi on 2. But since it's out of 12s, we just changed it to 6 pi out of 12. So each one I just added 6. That one I added 6, added 6, added 6. The asymptotes, I added 6, added 6, added 6. And then the x-intercept, I subtracted and added 6 to get all the x-intercepts. So if you put it all together, it just feels really simple from here that you just simply pull it down, just make sure that it kind of looks like the centers where the blue dots are. And the only thing I haven't got so far are, because the x-intercepts is over here, 26 So that means I likely would have a graph that stops somewhere there. Okay, it also means that this probably will hit the y-intercept somewhere here as well. So the only problem is I don't know these 2 points. That endpoint, this endpoint. Sub in 0 to the function to find that point, and sub in 2 pi to find this point, and that's your graph. You can see why tag graphs, when you add in all the transformations, it can take long because there's so many elements that you have to put in together. But one graph tells me a lot about your understanding of circular functions. It tells me the understanding of what you need to do to calculate, because it's problem solving. It's thinking about what I mean. That's why sine and cosine, for the first time when you're doing it, with all transformations year 12s, takes about 25 to 30 minutes to do for the first time. Usually a good speed is about 7 to 10 minutes. If you want to get everything correct and you're doing it all by hand. Otherwise, tag graphs are easy just simply because you only need to find one of everything and add the period. That's why it's easy. Sine and cosine quickly. We don't do that until year 12. This is 14K. Okay, so that was me showing you how you would actually go through step by step. But hopefully you're seeing the logic that I'm just going through. I'm just finding starting point, x-intercept, asymptote. That really already gives you most of the shape. We just stick to those 3. Starting point, asymptote, x-intercept. Just 3. But to get those 3, the x-intercept is the hardest. Making sure that you can know your exact values and symmetry properties. And then transformations to know how to read. Does it go up, down, left, right? That's different. So how much of that content have you retained since Unit 1? That's why I said if Unit 1 wasn't looking good, you move into Unit 2. We do repeat it all again. You either learn it or you don't. So in this last 6 months, by the end of this term, you'll have a general clear idea whether you want to continue with methods next year. Because that's essentially what we do, but faster. Yeah? So we teach you all of this, but much faster. All good? All right. Just to finish off, because you may not have known how to find the endpoints. For those who don't know, I'm just going to be explicit about it. The endpoints, the domain was between 0 and 2 pi. So I just don't know when x equals 0 and when x equals 2 pi what the actual answer is. And this is what you do. When x equals 0, you sub it in. So y will equal to, I think it was it negative or positive? 3. So 3 tan of 2x, is it minus as well? Yeah, minus pi and 3. Plus root 3, you're subbing 0. So it becomes y equals 3 tan of 2 times 0 minus pi on 3 plus root 3. 2 times 0 is 0. So you're really just working out 3 times tan of negative pi on 3 plus root 3. Now going back to your exact values. What is tan of negative pi on 3? Yep, so that's negative 60 degrees. So because it's negative, it means you're going clockwise. So clockwise 60 degrees. So you're down in quadrant 4. But tan of 60 degrees. What's tan of 60 degrees? Pi on 3 is this finger. Root 3. Okay, 3 sine fingers over 1 cos finger, and then square root it. So that gives you root 3. But because tan in that quadrant is negative, as you can see it's negative gradient, so it's 3 times negative root 3 plus root 3. Now let's work it out. That's negative 3 of these root 3s, and you're adding on 1 root 3. So how many root 3s do I have? Yeah, well, negative 2. Yeah. And so that gives me that endpoint, which makes sense. We predicted that it had to be a negative y-intercept. We just didn't know where. And negative 2 root 3 is probably a bit further than what I drew there. It's further down. So that's all it is. So we just got to label that a bit more carefully. Negative 2 root 3. Root 3 is about 1 point something. So if you double it, so it should be negative 2 point something. So we'll just put it somewhere there. So there's your endpoint there at when x is 0, you get negative 2 root 3. Then now you got to work out this side, 2 pi. Even though I technically know it's likely the same because of the period and all that. But let's work it out. X equals 2 pi. Same thing. y equals 3 tan of 2 times 2 pi minus pi on 3 plus root 3. That's the same thing as saying 3 tan of 4 pi minus pi on 3 plus root 3. This is the part that you've been practicing that I said was the prerequisite knowledge for solving. There we go. What is tan of 4 pi minus pi on 3? And hopefully you can use a unit circle to figure it out. 4 pi, every even pi you're starting at this point. That's where 4 pi is. If you subtract by pi and 3, means you're going anti-clockwise. Yeah, so if you're going anti-clockwise from 4 pi, so remember it goes 1 pi, 2 pi, 3 pi, 4 pi, but you're subtracting. So if you're subtracting, you're going back clockwise. So we go, you're going back this way. We're in quadrant 4 again. And it's the same thing. Tan of quadrant 4 is going to be a negative, and we're finding tan of pi on 3, which you guys just worked out before. You said it's negative root 3 plus root 3, and funny enough, you end up with the same answer. Negative 3 root 3 plus root 3 gives you negative 2 root 3. How did I know that the answers were going to be the same even before I did my calculation? Does anyone tell me? How did I know? I use some sort of logic, and I want you to be able to do that as well. What did I do that I looked at the equation and the domain? I say, yep, at 2 pi, it's going to land back at the same number. How did I know? Because we worked it out. 0, negative 2, negative root 3, negative 2 root 3. How did I know, even before calculating it, that it was going to end up at the same spot again? Anyone have a clue? How did I know 2 pi negative 2 root 3? Yes, Numafi. Yeah. It's mainly the period. What was the period again? Pi and 2. But you see, pi and 2, does it fit nicely in 2 pi? See, 0 to 2 pi. You start at 0, starting. So you had a value here. You had negative 2 root 3. In my head, logically, all I was thinking is 0 to 2 pi. Is it multiples of the period? If that's the starting point, pi on 2, it'll land back at negative 2 root 3. Then I do it again. Pi on 2. That's now at pi. It'll land back at negative 2 root 3. So then I said, oh yeah, well that just means by the time it's 3 pi and 2, same thing again, negative 2 root 3. And then by the time it gets to 2 pi, negative 2 root 3. Because all I'm doing is I use one value and I add on the period. Same idea. I just looked at how many times will it fit. If it fits perfectly, I know the answer is going to be the same. So try to analyze it to that kind of level. Understand the period is special. It keeps coming back to the same spot. If you understand that sense, then it's easy to get through quicker. Otherwise, you end up doing that twice. It's just a bit longer. Okay? All right, team. I'm going to stop there. It was